Hey, Cassidy, can you hear me?
Yeah, I can hear you.
Excellent. I can hear you too. And give it 60 more seconds. What's up, Corey? Hi, Hannah. Welcome. All right, let's do it. Okay. Homework 4, question 3. So 2 things before we actually get into question 3. I got a couple of emails that asked some good questions. So shout out Cassidy and shout out Hannah. I think that's where these came from. But I figured it's quite possible that other people have the same questions, so I'd go over those. So one was about little k versus big K, and whether in this equation for acoustic impedance, that K is a little k or a big K. And it's a little k. It's spatial frequency. Okay, so that's omega over C. So don't get that mixed up with, what's the big K called again? Bulk modulus, right? Yeah, that's not bulk modulus. That K is omega over C, spatial frequency. Cool. And I know I put that here. I didn't give you the equation for it, but at least I did say that K is spatial frequency there. Okay, so just in case anybody had that same question. Okay, and then someone else asked about peak values versus RMS values. Specifically, they were asking for the, where is that part where we convert? Sorry. Or, sorry, where is that? Right. Oh, here we go. Okay, for this part, right? So we know, we talked about that for a sinusoid, if you have a peak value, you want to convert it to RMS, you divide it by √2. And the question was, what exactly do you divide by √2? Is it the whole thing? And the answer is that you divide the peak value by √2 to get the RMS value. And if you're looking at something, and I want to go back down here, if you're looking at something in this form, a times e to the omega t, or omega t plus something else or minus something else, the a is the peak value. All right, so if I want the RMS value, I'm doing a divided by √2 here. The reason that that is the peak value, the reason that it has that name is that, well, I have so if I have e to the omega t, what's the real part of that? I just want to know I want to take e to the omega t and I want to take the real part of that. What would that be? Or sorry, there should be a j in there. Already is real. Okay, with the j, what would that be? Anybody have their Euler's identity on the tip of their tongue? What's the real part?
A cosine omega t.
A cosine omega t. So if I'm talking about e to the j omega t and I want the real part, I'm just talking about cosine omega t. And what's the largest that cosine omega t can ever be? 1, right? So the peak value, A, is the largest this whole expression can ever be. And that's why it is the peak, right? It's one of those things, it's like, it's useful, I think, to touch back on these super fundamental engineering concepts, because we get to this place where we use them without thinking about them, and sometimes you can lose sight of what they are. So A is the peak value, and that's why it's the largest that'll ever get. And then I wanted to take this opportunity to talk about RMS for just a second, and just because it's so fundamental to engineering and we use it all the time, and it may be something that we just, that's RMS without thinking about what it means or why we might use it. So we have this function, and let's just rewrite it as a cosine omega t, right? So that's going to look something like that, right? Pretty bad drawing, but that's okay. So the RMS value, what does RMS stand for? Root mean square, right? It's a little bit of a misnomer. They should call it square mean root, because that's sort of the order we're going to do this stuff in, right? So if I want to know the RMS value of this thing right here, this function, this cosine function, the first thing I'm going to do is I'm going to square it. And what is it going to look like when I square it? I'm just going to redraw it. I know that's sort of hard to describe. Anybody want to take a stab at it?
Well, first, the one below the x-axis.
Yeah, we're going to flip the whole thing, and it's going to become a little larger too because of the square, right? I'm cool with that. Yeah, that's probably true, right? Yeah, good thinking. Yeah, forgot about that. For you circuit-minded individuals, right? This is like rectification with a little bit of amplification, right? We're going to rectify this bad boy. Okay, so let's do it. So we're going to do, oh Lord, something like this. I don't know if I'm doing John Woo's like narrowing or whatever, but that'll work, right? So, for the point. So we did the S part. Now let's take the mean of this thing. All right. Oh, I'm running out of space. I'm going to do it right on the same graph. So let's call this the mean. I'm cool with that. All right. And then let's take the root of that. And the root of that is just going to make it a little bit lower, right? So here is my RMS value. You okay with that? And the reason we care about this, right, is because it's a good way to average things. We want to know the average of the amount we're away from zero. And we don't necessarily care whether we're away from zero in the negative direction or the positive direction. We want to know the power that it's carrying. That's part of what we're getting at here, right? Because the RMS value is what's going to determine like energy delivery, right? Okay, so I wanted to toss that in there in case it's been a while since you took a freshman level course that talked about what RMS actually is. But for this question, right, all you got to know is that you need that A part and you're going to divide that by root 2 and you're good to go. That only works for a sinusoid, right? That is not true for other waveforms, right? Not going to get you the RMS value of a triangle wave or a square wave. It won't work that way. Okay, cool. All right, let's actually talk about question 3. You are swimming underwater in a pool. A friend yells at you from above the water. Assuming your friend's voice behaves like a plane wave, normally incident to the water. What does normally incident mean?
Perpendicular?
Yeah, exactly. So a plane wave perpendicular to the water, what is the ratio of the reflected pressure to the incident pressure? And then we've got a couple of values, a density and a bulk modulus. Okay, cool. So I have collected for you all of the equations that you need. We're back to high school physics again. Here are the equations, plug in the numbers, do the algebra, and Bob's your uncle. Let's draw this real quick, okay? So, how did your friend end up normally incident? He's like above the pool somehow. Oh, he's on the diving board, maybe, right? Anyways, I just thought about that. Okay, here is the water line. Here is you. Okay, there you go. Maybe you have some flippers on. And here's your buddy, and he's just a bodiless face, and he is talking this way, right? And some of that's going to reflect, right? And that's what we want to know. We want to know how much of that pressure, what percentage of the pressure value of this wave is going to be reflected back. And what we're going to need to know is we're going to need to know the propagation speed in both mediums. We already know it for air, need to know it for water. And we can do that with conveniently the two values we've been given, the bulk modulus and the equilibrium density, I think is what that's called, rho naught for water. Okay, so you can find a propagation speed of sound and water. You need to know an impedance, Z equals rho naught times C. So once you have that C, you can find a Z. You need it for both, again, water and for air, right? And then we have a reflection, pressure reflection coefficient is what that's called. And all we need for that is the impedances of the two mediums, okay? I wrote it ZT and ZI in the notes. I think it's Z2 and Z1. I did T for transmission, so that would be water, right? And I for incident, and so that's going to be air. Okay. So let's draw that here. ZT, ZI, incident, transmitted. Everybody okay with that? Plug that sucker in, you're done. Is there a unit for that? I don't know. No, right? Because it's a ratio. I just decided that, so I don't know if that's true, but I don't think there's a unit. Yeah, because it's Z's on top of Z's, so the units are going to go away. I feel satisfied with that. Any questions about that? All set? Yep.
For the propagation speed.
Yes, sir.
Wait, never mind. It's just using, so our bulk modulus is our value of that would be K, big K.
That's big K, right? So it's a big K here. And that's just a value that's given to you, right?
Yeah.
And you already know C for air from the first question.
Yeah.
But you could run that again. He gives you actually more information than you need because he gives you the bulk modulus and the equilibrium density. So you could calculate C and you'll get the value he gives you. Anyways, is that okay?
Yeah.
All good? Okay. So I think that gets you done with that. Your friend is now yelling at you at an angle, and I found this adorable picture online with the yellow submarine in it, of 7.5 degrees relative to the normal. At what angle do you think he or she is yelling from? So let's just get straight with our angles, like what's what. So this, because I think that's almost more, like that's an easier way to get confused. Like you have all the equations for everything else. You just got to know what angles you're actually talking about. This, the angle is always measured from the normal. So just, if you remember that, you're good to go. This is theta I. Let's do this. This is theta I. And this is theta T. Okay, so if you can find theta T, we can draw one of those little dotted lines back up to here, and that's where you're going to think that that person is yelling at you from. So theta T is actually the only value that you need here. You don't have to do any subtraction from 90 or anything like that. Okay. Oh, Snell's law. You should probably know that. That's how you're actually going to find it, right? There you go. You got an incident angle, you have a transmission angle, you have a propagation speed in the initial medium, which is air, and a propagation speed in the secondary medium, which is a term that I made up. We're going to call that water. Okay. So there's a little bit of algebra here, but you're looking for theta T, right? And you have everything else. You okay with that? I'm gonna sit on that for a second, see if you have any questions. Okay. Now we're cooking with gas. Your friend is now seated on the pool deck, a distance of 4 meters away from you and 7.75 meters above the surface of the water. Can you hear anything he or she says? Let's just try to draw this. So here's the water. Okay. Here is you. You are a box. And your friend is like, so let's do that. Let's do that. Make sure I do this right. That's 4 meters, right? And then this, try to draw this to scale, is 0.75 meters, right? And this is your friend, your friend. Okay, so I would draw it out. right? And make sure you know the angles that you're looking for. It's going to take a little bit of trig here, but I'm sure you guys can sort that out, right? What the actual angle is, right? But that's what you really need. So if we draw this right here, yeah, I guess like that, right? We are going to get some angle here. Though the one that we need, and this is where you got to make sure you're looking at the right spot. This, sorry if this is getting messy, is theta I, right there. And you want to know how this thing is going to bend or what's going to happen to it. You need to find theta t, right? Obviously, hopefully that was clear that that's what's going to lead you to this answer here. So let's talk about how it's going to do it. As long as everybody's okay with my drawing. Pretty sure I did that right? I think so. 4 meters, 0.75 meters. Got an angle theta, incident angle. Feel good about that. Okay, can you hear anything? So in class, the professor talked about rearranging Snell's law using a trig identity to get something that looks like this here. And we talked about how funny things happen if the value underneath that thing, underneath the radical becomes negative, right? And you get the square root of a negative number and, things get strange. So the first thing you need to know is this thing called the critical angle, right? And the critical angle is defined thusly, okay? So find that critical angle, and once you know that, then we can look at some conditions to see what happens under those conditions. So if C1 is greater than C2, and we're talking about propagation speeds in the two mediums here, which you already know because you already calculated them, then that sound wave, it bends towards the normal is what happens. Theta t ends up being smaller than theta I. So, something like that, I guess, right? Something like that, okay? All the other, and that's true regardless of those angles, no matter what those angles are. All the other conditions have to do with when the transmission speed, the speed in the transmission medium, the second medium, is larger than the speed in the first medium. And then there's some caveats about how the incident angle relates to the critical angle as well. So in a condition where C2 is greater than C1 and the incident angle is the critical angle, then we're going to bend at exactly 90. So you could get like, this, right? Would be that scenario. This drawing's going to get messy. Okay. Because that angle would be 90. Then if, again, C2 is greater than C1 and the incident angle is less than the critical angle, then we're going to bend away from the normal now. And then there's this other weird scenario where C2 again is greater than C1 and the incident angle is greater than the critical angle, and we end up with total internal reflection, right? We talked about that plenty in class, but here is it all put together in a table for you. So if you so you calculate, what you're going to do here is you're going to calculate the critical angle, right? You know, or you can calculate theta I, right? You know C1 and C2, so find out what sort of, which of these conditions are true for this scenario, and then you'll know what happens. That sound okay?
For with C2 transmission.
Yeah. I wrote secondary medium here, propagation speed in the secondary medium. Sorry, I switched, didn't I? Yeah. CI equals C1, my fault. I guess I couldn't decide. Let's write that here. CI equals C1, CT equals C2 in this case. Sorry about that. Thank you for catching it. Okay there? Yeah? Internet, you guys good? Internet's always good. Corey, are you saying something? You just turned green. No, you're not saying something. Just, oh, you are.
I tried to. We're doing good.
Oh, dope. Thank you. Okay. And then that leads us to the last one. What is the maximum horizontal distance away your friend can be seated 0.75 meters above the surface so you can hear him or her when you are underwater? So we know when we can't hear him or her, right? That is this case. Yeah. So find out, do a little trig and find out when that ceases to be true, right? C2 and C1 aren't going to change, right? So you're really talking about the only thing you can really affect here is theta I, the incident angle, right? So find out when this little chunk isn't true anymore with some trigonometry, and you figured it out. Sit on that for a second, or ask me questions. Let's maybe redraw it. It's going to be the same drawing, but that's okay. So there's the normal. Here's the water. We want to know, I guess it doesn't matter where you are. I don't know why I keep drawing you. So this is the distance that we're going to be adjusting. We'll call that X, right? This distance is fixed. This is 0.75 meters, 0.75 meters. Okay. And then we have an angle here. Right, this makes an angle. And this is theta I, or 1, depending on what kind of mood you're in. And figure out that value of X where this is, this condition changes, right? When is theta I no longer greater than theta C? When does it become larger than the critical angle? That feel all right to you guys? Feel all right to you?
Yeah, can I just see the modified Snell's law?
Yeah, for sure. So this one, right?
Yeah.
Yeah. So this is almost here for edification. Like this is the Y kind of, but you actually only need the table to figure this out.
Oh, wait, yeah, I just read. We just have to do trig to find out what the angle is.
You're only like, I gave you a lot of information, but what you care about is theta I and how it relates to the critical angle, right? That's what's going to determine things here. You're not going to affect C2 or C1. That's, been
That's fixed unless
fixed. Yeah, you
pool salt.
yeah, you could dump a bunch of salt in the pool. You'll fill it with Capri Sun. I don't know. So I imagine Capri Sun's mostly water. It may not matter that much. It'd be a lot of work. Gatorade would do, because the electrolytes, certainly things would change in that scenario. That's a dissertation right there, my friend. That's it, man. That's the homework. Questions? Anything unclear? Yeah.
Yeah, like the equation where you put a star, is C1 in this case CI and C2?
Yeah, I that was pointed out. I realized I screwed that up. C1 equals CI. If you look at this right here, I made a little key for you because I messed it up. CI equals C1, and CT equals C2.
All
Sorry
right,
about that.
thank you. Yeah, and also, will you post this video today?
Oh yeah, for sure. And I will do that actually before I leave here because I know the homework's due tomorrow, and
Yeah.
so you guys might need that quicker
Thank you.
than later. Yes, thank you for reminding me. I'll do that as soon as I shut this off. What else?
I hadn't started question 3 yet, but it looks like we don't need any MATLAB for this assignment.
That is correct, sir. No MATLAB.
OMG.
I knew you would be excited. So you can always
I'm a
use
happy-
MATLAB to do your homework for you, Corey.
Yeah, I could. I really should, but I probably won't though.
Yeah, fair enough.
Thanks, man. I appreciate it.
No sweat. What else? You're good.
For the first question?
Yeah.
Part B, finding the sound pressure level
Mhm.
in DV, we're just using the Ruby squared coefficient, right?
So sorry, which one again?
For D.
For part D, question 1, part D.
Yeah.
Question 1, part D. Okay. Yeah, that's right here. So for SPL, it's just 20 log of the RMS value over the reference value.
Yeah, which not include, like just the real part of the
Yeah, so that RMS, you're going to find that, right? Like we were talking about, where you take it and divide the peak value by √2. In this case, it's 0.7, right? So it'll be 0.7 over √2 over PREF. Right? Isn't that right? Yeah. 0.7 e to the j, 3000 t. If you don't have any questions, you are absolutely welcome to take off.
Thank you.
Yeah, of course, anytime. If you do have questions, hang around. I'll answer them. Is that the value you saw, the 0.7?
Yeah, I took the square root of the particle velocity or the Ruby squared of particle velocity.
Oh, yeah. No, just the pressure here.
Yeah.
Yep.
Yeah.
Yep.
I got a way smaller number of it.
Bye, guys. Have a good day. Thanks for coming. Did you have a question? Anyone in the internet?
I just have a quick question about
Yeah.
the Munson curve. I just want to like double check that I'm doing it right. So like I have
for sure,
my
for sure. Yeah, let's go up and look at that.
yeah. So like I did D, so I have like my dB values. So I just want to make sure. So I have So I have it in dB. So then what I use the I'm like pointing, like you can see what I'm pointing at.
Yeah, totally.
So I would use the axis, the y-axis pretty much to get my value, and then do I go across until I hit a curve that it meets?
You have a frequency too, right?
Oh, yes.
Yeah,
I do, yes.
that's probably the missing link. So let me just draw this on here. We'll just do an example. So I know that I have an 80 dB wave at 100 hertz, right? So how loud is that in fons? Well, at 100 hertz, make sure I do this right. Hold on. I confused myself somehow. Give me like 1 second. I knew how to do this like 2 days ago. And it was very obvious. Oh, yeah. So that was a bad example because there's not a line there. So let's do one with a line. So let's do like 75 dB at 100 hertz would be right there. You see that? Sorry, let me draw that. 75 dB at 100 hertz right there.
Yeah.
Right. So that sounds like 70 fons, right? I just follow that.
Okay.
What line is that? Does that make sense?
Yes, it does. Okay, thank you.
Yeah, no sweat. I think it's helpful to like think about how this chart was made. And it was basically like, I played 1,000 hertz at 20 dB, and I was like, okay, keep that volume in your head. And then I'm gonna play like 20 hertz, and I'm gonna see how loud I need it to turn it up so it sounds just as loud to you. You know what I mean? So
Yeah.
at 20 hertz, apparently, I had to turn it up all the way to here. I needed 75 dB SPL for that person, or that, hopefully lots of people, to agree that it was the same volume as 1,000 hertz at 20 dB, if that makes any sense. But yeah,
It does.
cool. Any other questions?
No, that was it. Thank you so much.
Yeah, no sweat. Have a good evening, and feel free to email if you do run into questions.
Okay, thank you so much.
Yeah, of course. Bye.
Bye.
Yeah. So I don't know. This is a question that there actually is an answer to, so I don't know if I should be guessing.